Good morning, I'm Robert, and today I'll be presenting our recent work, Scaling IP Lookup to Large Databases Using the CRAM Lens. And this would not have been possible without the help from my collaborators from both UCLA and Cisco. So from our work, we kind of condensed it and we extracted 4 main takeaways, and these takeaways will be reintroduced several times throughout the talk. So regarding algorithms, we found that using both CAM and RAM synergistically together, as opposed to just one of the resources, it opens a brand new door and introduces a new research direction for future work into finding new ways to scale network processing algorithms. To facilitate this, we introduce a new complexity model we call the CRAM model. And the CRAM model enables one to make easy, quick predictions of performance for algorithms on chips like on RMT and DRMT style chips like Intel's Tofino 2. And it's accompanied with a set of 8 optimization idioms, which are really like design guidelines. And we successfully demonstrate and apply the CRAM model to the problem of IP lookup in this paper. And using CRAM, we're able to successfully scale IPv4 and IPv6 global routing table sizes by around 9 and 3x respectively when compared to TCAM-only approaches. And our results reveal the simple but powerful architectural message that a little TCAM goes a long way. We believe that network chip designers should strive to include both TCAM and SRAM in their chips going forward. So before continuing, I will introduce some relevant background. So for these chips, there's 2 relevant types of memory, TCAM and SRAM. Hopefully we're all familiar with SRAM, but a quick refresher would be for SRAM, the input is simply the address, a memory address, and the output is whatever value or content is stored at that address. For TCAM is the direct inverse, where instead your input is the content, or basically you're specifying what you are looking for or trying to match on, and the result is the address of the first match found. Right? And another distinction between TCAM and SRAM is that TCAM can support ternary or wildcard bits. These are often denoted with an asterisk or like an X in the picture, and these wildcard bits basically are like don't care bits, and they match on both 0 and 1. A simple example here would be if you're specifying for the TCAM on the left 10111, the first match going top down would be the third row 101XX because those are wildcard bits. And because it's the third row, you would simply return the address, which in this case would be 10. For SRAM, your input would be the address. So if you're looking for the value at the first entry 01, you would go to the second row, and then you would simply return 010. Likewise, there are 2 relevant different modern packet processing architectures, RMT and DRMT. The key difference to note here between the 2 is that RMT is strictly a sequential pipeline architecture. And notice that within RMT, within each stage, the processing is directly tied down to the memory, right? So stage 1 cannot access the memory in any of the other stages except its own memory. DRMT completely disaggregates the processing from the memory, and it puts all the memory in a pool, and it puts it behind a crossbar, right? So processor 1 could, hypothetically, if you wanted to, access the memory shown on the very right. And we note here that, in a way, RMT is a more specific version of DRMT with additional access restrictions. For our work, we mainly tested using Intel's Tofino 2, which is a RMT chip, but we're fully confident that our results can be easily reproduced on any DRMT chip. And these kind of chips are typically characterized by 3 primary traits. They come with ample amounts of both TCAM and SRAM. They have high degrees of parallelism, both within a processing unit and between identical pipelines. And they have a high degree of programmability, often with like a language like P4. So we had 2 primary motivations for our work. One is we noticed that there was a significant lack of an abstract model for quickly evaluating and comparing algorithms on these new RMT and DRMT style chips. For example, if you had multiple algorithms on hand and you wanted to tell which one could scale to the largest database, for example, then pretty much the only way to do it would be you would have to write out the P4 code for each algorithm, implement it, also come up with the control plane code. And for some algorithms, it's not that trivial of a process, right? And to make matters worse, we found that between different implementations of RMT and DRMT chips, there's a lot of hardware-level details that can vary greatly, and these hardware details are killer when you're trying to, and they can have a huge effect on when you're trying to map an algorithm to the hardware. For example, just naming a few, like how many parallel lookups can be supported per stage, how many sequential operations you can fit on a stage before it bleeds over and requires additional stages, basic memory dimensions, like how big is your TCAM block or SRAM page, and additional things like that. The second motivation was we really wanted to address the limitations that we saw with single resource approaches. So traditional SRAM and DRAM only approaches, a lot of them don't translate well to RMT architectures at all. Many don't even fit. And a lot of them are optimized strictly for the traditional RAM model, meaning they prioritize certain optimizations like early exits. They choose to avoid the additional latency cost of hashing by using more memory, paying a penalty cost in memory, and using directly indexed data structures, right? With TCAM-only approaches, they consume significantly more power, significantly more transistors per bit. They scale poorly, and a lot of the more advanced TCAM approaches, they actually require hardware changes, which is one thing we try to avoid. So how can we leverage both the CAM and RAM that is available in these kind of chips to revisit all of network algorithmics? So here we introduce the CRAM lens, and as a quick definition, the CRAM lens has two components. So the CRAM model specifically refers to the formal model definition, or model representation of it, and then it's accompanied with a set of 8 optimization idioms which really function as design guidelines. And so really the CRAM model is a formal model for estimating performance on RMT and DRMT chips. So a typical workflow or a way you might use the CRAM model would be you start with a base algorithm. You, depending on the algorithm, you custom fit it, and you apply a subset or potentially all of the optimization idioms, basically, and the product of that process would be a more RMT optimized algorithm that leverages both CAM and RAM in some capacity. And then from that, you build a directed acyclic graph representation, a DAG representation, where each node is something we define to be a step. And a step is defined merely as an optional table lookup, and that lookup can be exact or ternary in nature, followed by a sequence of independent operations. And that's one step. So that's each node is a step. And so the CRAM model becomes very simple to use. To compute memory, you simply sum up all the TCAM and SRAM bits across all tables. So TCAM, you would just add up all the bits across all the red nodes. To compute latency, you would find the critical path in the graph. And that would simply be the number of steps in the longest directed path that's present in the graph. So we mentioned earlier that there's 8 idioms, but to save on time, we kind of just introduced 4 to give the gist of it. So for example, compressed with TCAM, in certain cases, if you have a lookup table and you have many entries that share, let's say, a common prefix. So here with this example, all of them start with 1, 1. And so with these kind of examples, you can achieve a very high degree of compression when you switch over to TCAM, right? So you're going from 4 entries of 4 bits wide to essentially just 1 entry in TCAM of 1, 1 and then 2 wildcard bits. The opposite would be expanding to SRAM. Obviously, TCAM is significantly more expensive than SRAM, and it also comes in far less quantities. And so you don't want to overly compress with TCAM. And so there's cases where if you're performing the SRAM expansion, so notice the last entry, 111x, assuming every entry is at most 4 bits wide, that really only gets expanded into 1 more additional entry, right? And so in that case, expansion is what we call cheap. And so in that case, you're not able to justify the increased cost of using TCAM. Table coalescing is simply if you end up with a case with many, many, many small, tiny logical TCAM, so separate TCAM tables, and let's say each one contains 1 entry. For example, if your underlying hardware TCAM block can support 512 entries as an example, then you're basically, the 511 entries you're not using in each block is essentially wasted. And so a simple solution here is just to condense them all into 1 TCAM block by prepending them with a tag bit. So obviously the trade-off here is you're making the keys wider, but you're able to eliminate waste. Lastly, look-aside TCAM is this thing where, based on observations of a lot of algorithms, like using IP lookup as an example, a lot of algorithms leverage and trying to do special things for edge cases. So for example, in IPv4, it's very rare to have prefixes longer than 24 bits as an example, right? So we find that a lot of algorithms kind of do weird things to handle these longer prefixes, when in reality, if you have TCAM available, you can just plop all the longer prefixes into a TCAM table, very simple, and you just do a simple lookup in parallel. So it's mainly to simplify things. So now we show how we demonstrate how we actually use CRAM in the context of IP lookup. So first of all, why does scaling IP lookup matter? Well, based off our observations using some well-known global routing tables, we find that IPv4 continues to grow at a steady linear rate, while IPv6 has grown at a much more accelerated rate in recent years. And from trends, such as the graph shown here, we see that the IPv4 table will on the current trajectory, may hit 2 million entries within a decade. And so the next 3 slides will show how we use the CRAM model to create 3 new IP lookup algorithms. So SRAM is a very well-known IP lookup algorithm. It basically breaks the IP lookup problem into 2 components. It first tries to find the length of the longest match, and then once it finds the length of the longest match, it tries to retrieve the corresponding next hop, right? And it leverages the fact that, as we mentioned earlier, in IPv4, there's very few prefixes that are longer than 24 bits. Right? And so for SRAM, they do this additional thing called prefix pushing. Without going into too much details, it's complex and it's expensive, right? And it's best to avoid it. And lastly, so you do you check the bitmaps in series to determine the length, and then based on the length, you go into a corresponding next hop array using DRAM. And note, DRAM is not available in the CRAM model, so we want to try to eliminate that, right? So the first thing we do is we say, okay, well, if greater than 24-bit prefixes are so rare, why go through the trouble of prefix pushing? Why not just put everything in a TCAM table in parallel on the side, and your problems go away? So that's the first thing we do. So that's why the prefix pushing becomes kind of that red TCAM glucoside node. We leverage the parallelism for these chips to do all the bitmap checks in parallel instead to reduce the number of steps. And then we combine to eliminate the DRAM all the next hop arrays into one singular hash table for all the lengths. So DXR is another well-known IPv4 scheme. It only works for IPv4. And the idea is it treats every IPv4 prefix as a range, and more specifically, a set of range endpoints. And what it does, it does this initial lookup table with like a k value, a slice value here of up to around 20 bits. And it basically takes the destination address, it directly indexes into this initial lookup table, and based on the result of that, it sends you somewhere into this huge binary search table where you basically do binary search over and over on some designated interval in it, right? So here we do a similar observation where, well, if it's the 20-bit limitation that's restricting DXR to IPv4, we notice that, for example, for Tofino 2, if the TCAM block width is 44 bits, 44 is much greater than 20. And so just by switching this over to TCAM, we enable the algorithm to support IPv6 as well. And it performs quite well on IPv6, actually. So we switch that initial table over to TCAM. This enables us to support much wider entries there. And then, as you'll see, we actually switch the binary search table to a binary search tree because we find out that a certain optimization you have to make is in traditional RAM, it's easy to access the same memory block over and over, while in RMT, you cannot do that. Probably the most intuitive one is classical multi-bit tries. With this guy, you simply go per node on a node granularity. You hybridize every node. So for every node you weigh, is it better to use TCAM or SRAM? Compress with TCAM or expand to SRAM? You do that for every node, and at the end of that process, you get basically a hybridized try, where it's a mixture of CAM and RAM nodes. And as a final optimization step, you combine the small nodes together to minimize waste. So pretty intuitive. So quickly going over the results for IP lookup. So for our experiments, we used 3 different abstraction models. So CRAM model we already covered. It's the easiest. It's the most high level, zero knowledge of the data sheet required. We use this intermediate ideal RMT model that uses TCAM. So it starts factoring in general memory specifications like TCAM block sizes, SRAM page sizes, number of pipeline stages, and it requires basic knowledge of a data sheet. And then lastly, we actually create P4 implementations for Tofino 2, compile it for Tofino 2, and it accounts for all details. But the issue with this is we'll go into it, but we find a lot of hardware level details that you kind of only find out when you start actually mapping the algorithms on. And so contrary to the earlier picture, this actually just shows an example of a CRAM model representation, right? So this is the DAG that we mentioned earlier. So to compute memory for TCAM, you just grab the number of bits or the memory usage for that node, which is just 3.13 KB. For SRAM, you just add the 4 with the 4.58 from the hash table to get 8.58, and you just count the number of steps. So it's very simple once you get a CRAM model representation to get the metrics, right? So what improvements does the CRAM model actually predict? So comparing SAIL and RESAIL and multi-bit tries and MashUp, we see that RESAIL completely eliminates the need for DRAM. It completely gets rid of that 32 MB, and it does so with a very tiny amount of TCAM, right? And it also increases the SRAM by slightly over 2, but it's a huge win by eliminating the 32 megabytes. And it also greatly reduces steps from 26 to 2. A similar occurrence is seen with multi-bit tries. We reduce the SRAM by a factor of 2 with a small, tiny cost in TCAM. And here are the 2 takeaways are that we find that we can greatly improve an algorithm's scalability by using both CAM and RAM, and that in fact, for the best results, actually only a little TCAM is needed. So how accurate was the CRAM model? Here we found that the CRAM model predicts 2 steps, RMT predicts 9 steps, and Tofino 2, the implementation actually required 16 stages. And we found that this kind of ×2 increase was actually because when we wrote the code, we realized that on Tofino 2, you could only achieve a maximum of 50% SRAM utilization, so around ×2. For BSIC, we found that CRAM and RMT predicted 14 steps, but the actual Tofino 2 used 30 stages because, remember, if a binary search tree, we're doing the greater than, less than, and equal to comparison, the 3-way branching. We find that on Tofino 2, what per node actually requires 2 stages, so it doubles the stages. But the good news is it's still within a factor of 2, and this is no different from when you're using a system like Big O notation. So how scalable are our algorithms? We found that RESAIL scales to around 2.25 million IPv4 prefixes on Tofino 2, and that's 9x what a pure TCAM approach can do. And we find that the SRAM only baseline we use, which is the traditional SAIL, it actually runs out of SRAM completely on Tofino 2. For BSIC, we find that it scales to 390 IPv6 prefixes on Tofino 2, which is 3.2x what pure TCAM can support. In fact, the other SRAM baseline here, I-BST, runs out of stages this time. It's important to note that we believe our results can scale even further on our ideal RMT chip without these 50% memory utilization restrictions. So we can support table growth for another decade. And to conclude, we believe that this is not the final step of CRAM. I know IP lookup is probably not the most interesting topic as of now, but we believe that future directions for CRAM can include generalizing it to other hardware architectures shown here, and potentially more interesting network applications, such as packet classification, stateful measurement algorithms using P4 registers, regular expression matching, and in-network machine learning. And just to end, just recapitulating the takeaways introduced at the beginning. Thank you, and I'm gladly field any questions.